Okay, we observed this thing rotating. Every time the thing pointed at a person, the person would write down the count on a timer. The timer consisted of this bolt at the end of a thread, counting 1, 2, 3, 4, and so forth. Then everybody was asked to write down the count, the last count that they heard, every time I'll call it the beam, pointed at them, either end, okay? One end points, the other end points, one end points, the other end points. Okay, now, I took one set of observations, and these are in green. And this column is labeled T, I've got it in green. That's time in pendulum cycles. And we could convert that to seconds. All we have to do is time the pendulum. I hope the person who was doing that held the pendulum at a consistent length that could be measured. But in that case, we could easily convert all this to seconds, but we're just going to use pendulum counts. It's very convenient. So the observations, well, I wrote down every other observation so that between count 2 and count 6, the pendulum, or the beam, actually went through 2 half cycles. In other words, it went through all of 360 degrees. So these are the times at rotation increments of 360 degrees. Okay? Now I've got a column labeled delta t here. The delta t is the change between this time and this time. We have an interval then of 4 counts between 2 and 6, 4 counts between 6 and 10, only 3 counts between 10 and 13, and usually, things go to slow down. So you wouldn't really have a shorter time interval between these two, but you don't know exactly where the person was between count 2 and count 3, for example, when they wrote this one down, or between count 6 and count 7. So, there's some uncertainty just where people were within the interval, and there's a possibility of some errors. You probably wouldn't have a 5 and a 6 and then a 4 if it was counted with complete accuracy. But nevertheless, we're going to get some good data out of this. Okay, so we have the time intervals, and those are in, I guess that's kind of a brownish orange. So that's this column and this column. And we can see that these times don't change much for a while, but then they start changing. They start getting longer and longer and longer. The trend is for the time between marks to get longer and longer. Okay, then we calculate omega. Okay, that thing there is an omega. Now, we had to do this outside. The power was off, so we had to go outside, and I smeared that, bringing the thing in. That's an omega. It's written pretty much like this. Omega, not W. Don't call that W, and don't type it as a W. If you got to type it, type out OMEGA. If you know how to use HTML, of course you can do ampersand, omega, semicolon, and it'll interpret. You have to know how to use the editor. Okay, so that's not real relevant, but omega is the angular velocity. In other words, how many degrees per second, let's say, because I did this in degrees per second. So here's omega. Omega is in degrees per second. Now over here I'm going to do a graph that shows our omega values. But I'll indicate over here that it's in degrees per second. Okay, so it took 4 seconds, excuse me, for a complete revolution. That was 360 degrees, 4 into 360 is 90, so that's 90 degrees per second. And 4 seconds, 90 degrees per second, 3 seconds, 120 degrees per second, and so forth. And I think I calculated all these right to the nearest whole number in my head. So you can always check the numbers, but I think they're pretty much okay. Okay, well, in blue then we see are values of omega, the number of radians per second. We call that an angular velocity. So I'll even write that down, angular velocity. Okay. Then I wrote theta. Theta is how far the thing has rotated. Okay, so there was no rotation up to here, but then from 2 to, well, between the count of 2 and the count of 6, the thing did 2 half rotations, it did a whole rotation. Now rotation, as I hope you know, is 2 pi radians. In other words, 360 degrees is equivalent to 2 pi radians, okay? And there's some words I should put around all that, but you get the idea. Okay, so by the time we get to 6, we're at 2 pi radians. By the time we get to 10, we've done another 2 pi radians, another complete revolution, that's 4 pi. So that our theta, our angle, starting from the initial mark, from the initial number that was written down, the initial time that the beam pointed at the person who was writing this down, is 4 pi, okay? And then does another 2 pi and another 2 pi, so you got 4 pi, 6 pi, 8 pi, even numbers times pi, all the way down to 58 pi, which would be 29 complete revolutions. Okay, so that's what these numbers mean. Now, you know, I wrote this out outdoors with the idea that we'd be able to complete this exercise, and then somebody came along and said the college had been closed, so we had to stop. So this might not make a whole lot of sense, which is why I've been careful to do the whole explanation. Now, what we want to do is a couple of graphs. We do omega in radians per second versus t in pendulum cycles. Kind of ran out of board there. And then we're going to do theta, which was in red here, and I probably should have used the red, but I think I did this kind of hurriedly after we were told to stop class, okay? But theta will be in radians, where t is again in pendulum cycles. Okay, well, we can put these points on a graph. Now, I'm not going to make you watch me put all these points down, but let's just do some select points. I've already, got up to where I'd had 3 points, and that would be the first 3 points. I kind of got 120 in the wrong place there, so you can correct that, but it's not going to make much difference. Should have been the third mark instead of the second, but that's okay. Okay, so we have 90s all the way over to the 45-second mark. So 45 seconds, there's 60, 50, 45s about here. So we pretty much have a bunch of 90s all along here. Okay? Then we get a little less. We go down to 72, 60, 90, 72, 72. Okay? So, I'm not going to mark these with complete accuracy. It would take too long. But the typical result in this block of results right here seems to be around 72, and the middle of that block is around 60. So I'm going to say 60, 72. 72 would be here. Here would be 60. Okay, then we have some other marks here. Some of them are a little higher, some of them are a little lower. So it might look something like this. We had a 72, and then a 60, and then a 90 up here, but mostly down here in the 60 to 72 range. Okay, so we're going to have some marks there. Now, of course, for homework, I'm going to ask you to do an accurate graph. Okay. Then we're dropping into the 50s, a 30, and a 60, and so forth. And by the time we get down to 168 or 180, we're down into the 30 range. Okay, and then we have, you know, up, down, you know, whatever along here. So our graph is going to look something like this. And then you're going to be asked to draw a straight line that follows the trend of this data. Now there are a lot of ways to draw a straight line. You get something kind of straight. Let's see if I can get these separated. Let's see here. Yeah, I can do that. Okay. It's just a chain of paper clips that was laying there. Okay, so I can see that if I put a straight line along about here, I'm coming pretty close to all, you know, kind of on the average, I'm coming as close as possible to all the points. So it's kind of a clear trend, the way I've drawn this, to the data points. Okay, so that line would indicate the trend of these data points. Now you're going to be asked for homework to find the equation of that line and so forth. Okay? And hopefully, you know, your mathematics is up to doing that since this is a calculus-based course. Okay? Or even a pre-calculus based course. Okay? Because we do have the option in this course to do it for a pre-calculus based course credit, a general college physics credit. But since everybody's had the calculus background, and that's what our university physics course requires, we're going to do it from the calculus point of view. Okay. So we got theta in radians, t in pendulum cycles. We want to do that graph. Okay? And it might be a good idea to switch over to the color that matches the data. Okay, I'm not going to bother overriding the radians and pendulum cycles. And we can, again, line off 240 here. Half of that is 120. Half of that is 60. Halfway between here and here is 180. And then we can not doing this all that carefully, and certainly not all that accurately, but there it is. Okay? So, is the camera on yet? Camera's still on, okay. So, we've got a graph here, okay? And we can put points on that graph. 2 pi happen at 6. Now, the radians, okay, I'm going to say 60 pi here. Cut that in half, that's 30 pi. And then I'll do 20 and 10 and 40 and 50. Okay, so at 2 pi, the time was 6. Now 6 is over here pretty close to the axis, you know, inside the 10 mark. And 2 pi, that's 10 pi, 2 pi is going to be here, so that's going to give us a point like somewhere around here. Okay? Now, I'm not going to do a whole lot of points. I'm just going to skip down to 60, let's say, and we're 28 pi. So at 60, t equals 60, we're 28 pi. We're all the way up here. There's 60, there's about 28 pi. And then when we get to 120, well, we've got 124, and we're at 44 pi. So a little over 120, 124, and 44 pi would be about here. So it's going to be like so. Then 180 is at 54 pi. And 54 pi is going to be up about here. Now that 44 pi, the 40 was a little bit low, so this point really ought to be a little higher. I'm kind of fudging because I know what the curvature of this thing ought to look like. Anyhow, 240 occurs at 58 pi. At 180, 80, it was at 54 pi, so it really hasn't gone up much at all between 180 and 240. So you have points like this. And you're going to get other points in between here. They're probably going to be a little more smoothly distributed. So if we've got all these points, we want to draw the curve. A straight line isn't going to fit this very well. So we want to draw the curve that best represents the data. Now I'm going to put the data in kind of like this, just to demonstrate. The data might be spread out sort of like this. Because I've just got the 4 points, the temptation is just going to be to go through all the points. The curve is not actually going to exactly fit any of the points, because if you take it down to the microsecond, it's just not going to fit all the points. We'll talk about that a little more. So I can draw a curve here that kind of goes through the middle of the distribution of the scattered points, and that's our best guess as to what was really going on with that beam. Okay, so now we have a curve. So we have a graph of theta versus t and omega versus t.